Welcome to The Explainer. Today, we're going to trace the incredible journey of something we use every single second but almost never think about: electricity. We're going to follow it from a massive, powerful waterfall all the way to the plug right there in your wall. But first, just take a second with me. Imagine if right now everything just went dark. The power goes out, not just in your house, but everywhere. What's the very first thing you'd miss?
For most of us, it's this. The world would instantly, and I mean instantly, plunge into darkness. Our most basic tool for pushing back the night, poof, gone. Then you'd realize your connection to, well, everyone is gone. That little supercomputer in your pocket, it's now just a very sleek, very useless piece of glass and metal.
And with that, the whole digital world just blinks out of existence. No remote work, no shows, no news. It's kind of staggering when you realize how much we depend on this invisible force for literally everything. So, to really get a handle on our world, we've got to get specific. When we say the word electricity, what are we actually talking about? You know, in physics, it's not some kind of magic. It's a real physical thing. And at its heart, it's pretty simple. It's a form of energy that we create by getting tiny charged particles, electrons, to all move together in the same direction. That coordinated flow is what we harness to make things happen. Okay, so how do we get all those little particles moving in the first place? Well, for that, we have to start big. I'm talking industrial scale power plant big. Check this out. This is a hydroelectric power plant. It's just a colossal piece of engineering designed to capture one of the most powerful forces on Earth, the energy of moving water. The whole process is this beautiful, kind of elegant dance of energy. First, you have the kinetic energy of all that moving water pushing against giant blades. That turns into mechanical energy as these huge turbines start to spin. And finally, those spinning turbines power a generator, which converts that motion into the electrical energy we can actually use. Now, let's contrast that with a completely different animal, like this coal-fired plant. The end product is the same, electricity, but how it gets there couldn't be more different. See, instead of using the energy of motion, these plants use heat, thermal energy. They burn coal or use nuclear reactions to create a ton of heat. That heat boils water into super high-pressure steam, and it's actually the steam that pushes the turbines. So one starts with movement, the other starts with heat. And that difference in how they start, it has a huge, huge impact on a really important factor: efficiency. In other words, how much of that original energy from the falling water or the burning coal actually becomes electricity we can use. And whoa, the difference is pretty dramatic. Hydroelectric plants are absolute champions, converting about 85% of the water's energy into electricity. Now, look at the others. Fossil fuels, less than half as efficient, and solar panels come in at just 15%. In those cases, a massive amount of the starting energy is just lost, mostly as waste heat. Seeing it as a bar chart really drives the point home, doesn't it? That hydro bar just towers over everything else. It really makes it clear how much more effective that direct motion to electricity process really is. Okay, so we've seen the big picture. Now let's zoom all the way in from the power plant right down to the tiny electrons themselves. And to do that, we have to talk about one of the most famous and longest-lasting mistakes in the history of science. So way back in 1752, Benjamin Franklin made a really logical guess. He figured electricity was like a fluid that flowed from a place with too much of it, which he called positive, to a place with not enough, which he called negative. It was a fantastic theory. It just happened to be completely backwards. It took nearly 150 years until a guy named J.J. Thomson discovered the electron, and science finally realized the tiny particles doing the moving were actually flowing the other way. And this is that legendary moment. Franklin, flying a kite in a thunderstorm, to prove this wild idea he had, that lightning wasn't some magical act of the gods, but just a really, really big spark of electricity. Insanely dangerous, don't try this at home, but it laid the groundwork for everything we know about charge, even if he got the direction wrong. So, here's the wild part. Because science ran with Franklin's idea for 150 years, everything, all the books, all the diagrams, all the math, was written that way. So when they found out it was wrong, instead of rewriting everything, they just didn't. So today, engineers still use what's called conventional current, which pretends the flow is from positive to negative, even though we all know the actual electrons are flowing the other way. Kind of crazy, right? Now, here's the thing.
Regardless of which direction you imagine it flowing, electricity always follows two very simple and predictable rules. A physicist named Gustav Kirchhoff figured them out, and they are the absolute foundation of all modern electronics. Kirchhoff's first rule, the voltage law, is basically like balancing a checkbook. All the energy the battery puts into the circuit has to be used up by the things in the circuit. Energy in has to equal energy out. Simple. His second rule, the current law, is all about what happens when a wire splits into two or more paths, and we're going to see that in action right now. And these two laws are exactly why the two basic ways you can build a circuit, in series or in parallel, act so completely different. And trust me, understanding this difference is the key to, well, pretty much everything you plug into a wall. Here's a fantastic way to picture this. Just imagine people trying to get into an amusement park. The flow of people, that's your electric current. And the turnstiles that slow everybody down, those are like resistors in a circuit, like a light bulb or the motor in your blender. Okay, so in a series circuit, it's like one long, single-file line of people going through several turnstiles, one after the other. The flow of people, the current, is the same everywhere in that line, but the energy they have, the voltage, gets split up and used a little bit at each turnstile. Now, a parallel circuit, that's like opening up a bunch of turnstiles side by side. The flow of people splits up between them, but every single person gets the same full amount of energy or voltage to get through whichever turnstile they pick. And that brings us to our final big takeaway. Your house, right now, is wired in parallel. So, knowing what you now know about voltage, why is that such a good thing? Just think about it. What would happen if your toaster, your TV, and your lights all had to share the same voltage in one single line? The answer is right there in the physics. Thanks for joining us on The Explainer.